Welcome, everybody. I'm going to try to be short because we're running a little bit late, and then there is a talk after us. So today we're going to have a talk about, alternative energy. I think it's important. I think if we really want to make a dent in CO2, we need to be looking at some serious stuff as well. And for this purpose, we have today Dr. Joe Borrometti, and he is a NASA chair professorship. He held a NASA chair professorship position at the Naval Postgraduate School. He worked at NASA for 10 years as a technology manager, lead systems engineer, nuclear specialist, and propulsion researcher. He's basically a rocket sciences guy. He there managed the emerging propulsion technology area for in-space systems, the Marshall Air Launch Team, as well as a variety of other power and propulsion assignments. After earning a doctorate degree in mechanical engineering from University of Alabama in Huntsville, he spent several years as a research scientist and senior research engineer at the UAH Propulsion Research Center, where he served as a principal investigator and manager for the Solar Thermal Laboratory. He has worked as a senior mechanical designer at Pratt & Whitney, supporting aircraft engine manufacturing, and at the Lawrence Livermore National Laboratory within the Laser Fusion Program. He's a graduate from the United States Military Academy. I think you'll find out that he knows what he's talking about, and I am eager to hear what he has to say. So please give him a warm welcome. Thank you.
Thank you. That was a great introduction. It's a blessing to be here. I have a lot of material to go over, so I'm going to dispense with some of my normal comments and jokes and go right to it. I plan to be talking about this in context of fusion, but I'm going to hold back some comments for there to get through the material and get to questions. One note in the beginning, I'm come here as an individual. I don't represent any agency or organization. There's a loose-fitting group of people around the country, mainly specialists, technologists that are interested in this field, both in energy and in particular thorium, and that we all have day jobs, fortunately good-paying day jobs for the most part, and so we come to give this information out freely and examine this idea and the use of thorium as an energy source. Outline, just going to mention that I talk about systems engineering because I've taught that as well as my thermodynamics and nuclear background. You'll see a little bit of that. Some assumptions. I'm assuming that most people understand the energy crisis. It's global in nature. It's nobody's got a quick fix, at least nobody who agrees what the quick fix is. Thorium is not going to be commonly known, especially as an energy source. Increased electrical capacity is very important to the overall energy consumption. And the last thing is energy equates to the state or the standard of living. And one of the last green energy forums I was at listening to, they equated to 58 slaves, if you will, working full-time at hard labor, 365 days a year for each person in the United States. And you can see that that level of energy is what gives us the standard of living. This slide comes from Lawrence Livermore Laboratories. It's one that I would spend a long time on. I think it has a lot of great points to be made. I would just say that if you don't know what a quad is, 10 to the 9th BTUs, it's a lot of energy. And if you just take all the energy we have in the United States and break it up into 100, you get 100%. So you can see oil is around 40%, and that line is the thickness equivalent to that. So you can see that most people would say we want to increase these desirables, okay? And notice the desirables are pretty thin, and it's kind of hard to increase them. These are the ones we probably want to phase out more, as well as less oil. We have huge energy losses in electricity production, about 25% efficient overall. Conservation is great. Do it at home. Most engineers, if they don't have to create any increased entropy in the universe, they would like to minimize that. But at the same token, you can see that we've paid the price up here, and that conservation, as much as we want to, there's not a whole lot of gains there in these two areas. The other thing is, if you notice right here, you can't make that line go to zero. Thermodynamics says you always have to have a cold sink. You always have to move energy. One example I talk about is wind, that you can put up a windmill and you can put another windmill behind it and you can extract a little more energy and slow that air down. But there's a fundamental limit. If you put too many of them in there, you not only get the last one to not move because there's no airflow, okay, you've actually affected all the windmills in front of it until you get no energy. So there's a fundamental limits to thermodynamics. You always have to have some loss there. And of course, most people would consider that you want to increase the electricity flow into cars or transportation areas as well. So what you really want to do is, if you can't grow these things fast enough on the order of this size, you really want some new energy source, something big, something that comes in, can be readily built, and provide that very big wide line. Something like fusion, right? Everybody would like to see that. Well, I'm here to talk about thorium and whether thorium can be that line, and also what's the best way to extract that energy. Now, without getting into a lot of details, you can take a little bit of thorium, put it in a normal reactor, and you get some benefits out of it, okay? But it's not an end-all, and it doesn't extract all the energy out of that thorium that you'd like to. And it doesn't mitigate all the problems you have with today's nuclear power. Thorium, just for background, is an element. 1828 it was discovered. It is slightly radioactive. Got a very long half-life. That's why it's around. And it provides your background radiation along with uranium. Most of it comes from that, just a little bit of thorium that's always around in the soil and in rocks and minerals. The only thing I'm going to say here is that thorium is not really commercially used for anything of much these days. It is a metal. It's got a very wide liquid range, some other interesting properties. I'm not going to go into any other details to know that commercially it's not a big deal. Now, this is a log scale of what's available in the Earth's crust, and you see that at the beginning you have oxygen, silicon, aluminum. Down here at 100 parts per million, in this box here you have copper in the middle. And towards the bottom, you got lead and thorium. And you can see I expanded this little area out. Uranium's about 4 times less than thorium. Boron, which some talks have, even at Google, talked about fusion using boron. All right, it's there. It's readily available. But what's interesting is the uranium that you're really interested, the one fissile material, actually split, is way down here, orders of magnitude less. So thorium, on a theoretical basis, the United States has about 20% of the world's reserves. To put this in perspective, one would say if you replaced all the energy, electrical energy generation in the United States that you saw before, and I'm not suggesting we do that. A lot of other energy sources will play, but that's about 400 metric tons. One mine can produce about 500 metric tons per year. You can see that's 10 times the amount. The United States has actually, the government has buried a bunch of thorium. They didn't know what to do with it. After paying for it and storing it, they just put it in the ground, literally, in these casks. You can imagine that's, even at this huge amount energy usage, that lasts 8 to 10 years. In a practical sense, this would last us probably 25 to 50 years. And you certainly have plenty of thorium available around the world. That's not enough. Like fusion, we can go to the moon. Difference is there, we don't have to mine the entire surface looking for it. Thorium gives a nice signal, and you can detect that from space, and so we can map it, and where the hot spots are, you know that there's a pretty good thorium deposit there. Same with Mars. So we know it's out there in the asteroids, thousands of years worth of power. Now, because of my systems engineering background, a little bit of the flavor I'm going to give you is in the vein of how do you select things or systems engineering criteria. And this comes from the aerospace, that about 80% of a project's life costs and benefits are going to be locked in the first initial decisions you make. And that pretty much, for all technologies, especially high-tech technologies, that holds pretty well true, 70, 90%, somewhere in there. And the reason is that it sets your theoretical limits. It also, at the time, you have your least real-world knowledge of how you're going to build or how you're going to go about doing this project. So the thing I try to teach is you look for the inherent barrenness, something untouchable, at least reasonably untouchable, and a growth factor that your concept will gain and exceed what your goals are. So let's take nuclear technology as we see it today. You know, list the pros and cons that are shown here. Most people recently have looked at, no greenhouse emissions, and that's because, in this case, about a third comes from electricity, and the far majority of that is coal. Nuclear doesn't have that. Now, to be very honest, one would have to analyze, well, how much resources does all this make when I go to build a plant, and how much CO2 do I produce? In the case of a nuclear energy, there is some, but over the lifetime and the amount of energy a nuclear plant produces, this is probably pretty a fair game to say it produces no CO2. But it's something you need to be honest about and compare. What if you could take some of the cons out of there, the safety fears and long-term sustainability and terrorist or proliferation issues, and make them go away, or at least minimize them? Sounds like what fusion wants. Another thing on systems engineering is concept of power density and efficiency. I can't go through all these, but obviously land usage, the maintenance costs, anything that you have to deal with, the overall cost of the lifetime of the project, smaller is not just convenient. It drives 90% of the time, it drives the cost. And therefore, at least the social cost, maybe not in a particular market, but across the board it usually does. And you'll see that that's very important for power density and efficiency. An example that comes into mind is the cost of material, labor, and then the distance from the end user, and all these other factors that factor in. I'm not going to go into big detail. This is information that's available and been readily been talked about. Natural gas turbine engines is about 1/10 the amount of steel, for example, in a nuclear plant. And a nuclear plant is actually pretty good compared to some of the others. But you see that in recent years, what are we building? We're building these very expensive, difficult, gas-using machines that are pretty high-tech, yet we're building more of those. Why? Well, because overall, the resources necessary to produce that and to meet the demand now makes you go for these things, and that's what's been happening. So in the light of what fusion wanted to be, safe, proliferation resistance, etc., that was one of the jokes. Today we have basically large plants, although there were a couple of Google talks that talking about making fusion in a way that's smaller. I would love that to happen. But basically we've got these very large plants, and of course they produce a lot of energy, but they also absorb a lot of energy in producing the energy. So your net gain is not as good as you would want. Kind of get into the history as well as the physics at the same time and talk you through a little bit about thorium and why we ended up with the lifter concept. Three basic nuclear fuels. Everybody should know, uranium-235 is what's naturally found. That's what we can start with. These two have to come from fertile material. We have to make them. They're not found in nature. And in history, everybody was working on weapons. And so you have an enrichment facility. You need a weapon design. You need fabrication techniques. For the uranium-238, you need a neutron source, which also usually starts with the uranium-235. You chemical separate. You need a new weapon design, new fabrication techniques. You get a slightly better bomb. That's all I will say on that. And thorium, well, they discovered you need the same thing you need with the uranium-238, chemical separation, but then there's some contaminant in this, usually, in which you go to an enrichment facility, but it's a hot enrichment facility. You need yet a new weapon design and new fabrication techniques to get the same kind of bomb. Well, obviously, these two are what the world has chosen to work on. Well, at the same time, most of the people that worked on those projects also were good people trying to say, what good can we do besides weapons? And electricity production was one of them early on. And they had the same problem. They had the same materials to start with. You need enrichment or heavy water production, a fuel design, okay, a little bit different, but it's still solid fuel, fabrication, and then electrical power. I say short-term electrical power because at the time, they really underestimated how much uranium-235 was in the world. There was a little bit more than they actually are accounting for originally. But at world usage, at the U.S. levels, it's still a very true statement to say, you know, there will be peak uranium if you base everything on uranium-235. Well, you can go with breeders. Fast spectrum breeder reactor. You need some sophisticated controls. We'll talk about that in a little bit more. Some fuel design, and you get electrical power. But you also get a whole lot more production of plutonium, which can use for nuclear power and run other reactors to produce electricity. Or, of course, you can use that for weapons. Thorium, on the other hand, looks a little different each time. Thermal spectrum, chemical processing, and you get electrical power. Very hard to get any extra out of it, and I'll explain that here. Enrico Fermi argued for the plutonium-based economy, essentially. And one of the reasons is you get 3 neutrons on average per fission. And the real key number you want to look at is this blue line, and that is the number of neutrons that come per absorption. And you need at least 2. You need 1 to split and 1 to breed your next fuel. And so, in reality, you need a little bit more than that because losses through the reactor, you've got to make it reasonable. So you have to work this thing. It doesn't work here at all in the thermal spectrum. You have to work up here in the near the what I call the bomb spectrum. Okay, you're using the fast neutrons coming off the reactor from the fissions. You're not slowing them down in a thermal sense. And you can see that this number really climbs very good, which means you get a whole lot more than 2, which means you get production of plutonium, or you can use it for production of plutonium. Well, Eugene Wigner at the time argued, well, you know, that's great for weapons, but we really want to base our economy on thorium. It's more available, and more important, it runs on the neutron spectrum, the thermal spectrum, such that it's a lot safer, a lot easier to control. You can use these reactors. This is a very difficult reactor, a very touchy reactor to work. But of course, it doesn't produce much because you see the average from the fission is only 2.5, and the actual absorption average is a little bit below that. Okay, so you're above 2, which is enough, but with real losses, you're not going to breed a whole lot of extra material out of this system. Well, historically, what did we do? We went from weapons to the Nautilus. There was Eisenhower's Atoms for Peace program, which was trying to say, well, we spent all this money, we want to look a little bit better in the eyes of the world, let's produce electricity. But you're using the same infrastructure, the same people, the same needs and desires. You pour it into here. At Shippingport was our first electrical plant, and sure enough, that is the base product for our surface ships. So a little bit of entangled there. It wasn't exactly Atoms for Peace in a conventional sense of what's the best way to produce electricity. Well, is that a good or bad decision? Well, I'm not sure I want to sit here and debate that, but you know, at the time, urgency of war, the fact that the weapons were unsophisticated designs, you needed a lot of material for it. The delivery systems were horrible, okay? And so you needed a large number to be a credible defense. Safety, environment, those kinds of things weren't considered as much. Compared to today, obviously, with very efficient designs, ICBMs are highly accurate, the need to scale down. We almost have too much material for weapons. And, of course, safety, environment, proliferation issues are the big concerns. Maybe it was right then, maybe wrong today. People can decide that. Well, in the tail of the nuclear reactor, thorium, engineers don't want to give up. When they see a good idea, they dog it, even though programmatically and the money and the funding was completely cut off. They went around, they said, look, Air Force, you don't have ICBMs yet. You need a credible defense to get your weapons out there, something that could fly a long time. How about this nuclear airplane? Now, the only way that this would ever do in a normal reactor is if you had a liquid reactor. And so they started a program. They sold the Air Force on it, as crazy it is. And I understand that somebody recently has said something in England, I believe, about this. I would not like to see nuclear airplanes as our base of commercial flight. I can talk about that at some other time for the reasons for that. But this reactor program started out, they did 100 hours, a high temperature. I believe that may be still a record, certainly for the overall reactor running that long, that hot. and that's 1,500 degrees Fahrenheit. Very much hotter than most reactors can run. Two things that came out of this. One, the fission products were naturally removed as you were pumping at it, which was really nice, and get rid of the poisons. And two, the load following capability, which was essential for the airplane application, and the fact that you wanted to throttle something without control rods, have instant response from the reactor, and then throttle back if you needed to get your power. This reactor in the fluid method was able to do that unlike unconventional or conventional reactors. Well, that program died pretty quickly as soon as the Air Force realized they could do the job much better with missiles. Missile program went full ahead, and that one was canceled. The engineers still wouldn't give up, okay? They hunkered down in Oak Ridge National Laboratory in a small program, but they ran a small program from 65 to 1969. And the main thing I'll say about this, without going into great details of the molten salt reactor experiment, was the fact that they ran it 24 hours a day, 3 shifts every day, but none of the engineers wanted to stay for the weekend. So they shut it down on Friday night, and they started up regularly on Monday morning. Something that's totally, not even thought about today in nuclear power plants. It is a base load. When it goes down for a long time. You don't get to restart it. The end result today, most people think of molten salt as this gigantic reactor, something very large. They even have some control rods that's so large. Single fluid, which means your thorium is thrown in with your uranium in the reactor itself. And you do have a processing system. You have a freeze plug, which I'll show a little bit later. And you have this Brayton closed cycle turbine system, unlike steam, that is an advantage to this idea. Well, if this was so good, the common question is, why wasn't it done? Well, hopefully I kind of hinted at that along the way. The establishment of the plutonium industry and the needs there. The fact that this is a liquid system, it's daunting. It's different than just nuclear energy. It's a lot of chemistry involved. There's an existing mindset that had to be broken. And Dr. Weinberg, who also owns the patents for the reactors we have today, who helped basically train Admiral Rickover and suggested what the reactor for the Nautilus was, he was hoping that this reactor, which he worked on for a long time, would be the eventual power reactor technology that would be used for electricity. Another person in his memoirs, deputy director at Oak Ridge, also pointed out that it was an Oak Ridge project, and therefore it was considered just their own pet project, and it was very hard to break out of that mold. Again, the existing bureaucracy. I've heard a lot of talks on the fusion as well, the same kind of mindset where you're trying to break what the common large program has in the government. All right, why is it so different? Liquid core, I mentioned that. The fact that it is thorium and that you have this chemical processing system. And you can see at room temperature, this is a crystal, it is a salt. And when you heat it up, it becomes a liquid, a little bit thicker than water. You can pump it around. Last thing on the history, Admiral Rickover in his program, he managed to put together a gigantic organization to build not only the Nautilus, but the whole nuclear navy. And it stands today. He's done a very good job as far as establishing safety record. The Navy is excellent in that. But understand, inherently, it's not found in the reactor. It's found in the very strict rules, the blind obedience, the very well-trained, long-trained process that you have to do with the sailors that run these reactors. So here's the path that we've taken, the typical nuclear reactor with this giant vessel. And the question is, have we made the best decision then, or are we making the best decision now? And I'm going to then propose that lifter is something that is what fusion promises. Some technical details. Lifter is a technology, or architecture of a technology, I should say. It's not a specific design, but it has certain design characteristics. 2 fluids. The fact that it's atmospheric pressure, very low pressure on the vessel. It's going to be high temperature. It's going to have chemical extraction. I'll explain why that's necessary. Thermal spectrum, and then the closed cycle Brayton system instead of steam. The reason why you have, this is the chart of the nuclides, the reason why we have to have extraction is that thorium with, this is protons 90, absorbs a neutron, becomes thorium-233, which beta decays in 22.5 minutes. Everybody know what beta decay is. Goes to protactinium. Protactinium, 27 days half-life. It also beta decays and becomes your fissile fuel, uranium-233. That's what you want to get in your reactor for your... Now, what if we leave the thorium, the protactinium in the reactor? This is what happens. You get the same beginning. You get thorium, beta decaying to protactinium. But now you have the problem of absorbing a second neutron, which is fairly highly likely, and 7.5-hour half-life. It will also beta decay to uranium-234, which is not fissile. Now, you could absorb yet another neutron here and jump to 235, and with another neutron, split the 235. But obviously, that chain is using way too many neutrons, and the reactor would stop under those conditions. And there's all these probabilities of how much absorption, and there are other decay methods that you have to take into account. So that's the main reason why you want to take out the protactinium out of the reactor. So the architecture for lifter starts out with the minimum core of fissile material that's hot. The four corners just kind of remind you the basic premise. What are you trying to, the goals you're trying to get to, which is a safe, compact reactor, something that proliferation resistance, waste reduction, covers that amount of electricity you need, that great big blue line, and do it quickly, as well as cost-effective, being effective connecting to the grid. So the core is just hot. You can pump it in and out, drives the turbines. Understand that. The blanket around it reflects the neutrons back in, or the thorium that's in the blanket absorbs and becomes your protactinium. You have to take out the protactinium. Here's the chemistry. And then let it decay, and then that produces the U-233. And you can actually extract the products, the fission products and other things out of the reactor as it's running in this liquid state. Look at the inherent advantages. Again, systems engineering, everybody has desired goals, and you kind of specifically list, well, what are those goals were the cost? Well, it's a low fuel price, low capital costs, long life, low maintenance, those kinds of things, transportation. You break those all down, and then you trace out what your inherent properties are to those, and you see whether you're matching up or you're getting what you really want to. So if we pick a couple of these, here's liquid core. You've got homogeneous mixing, which means you don't have any hot spots, which is a real concern in conventional reactors. One spot gets hotter, and it continues to get hotter until you have a meltdown. You get to burn up all the fuel because it's constantly being moved around in the reactor, and no fuel shutdowns because you can fuel this continuously. The expandability of the fluid gives you a large negative temperature coefficient, which is where your safety is at. No separate cooling system. That's one less system. And the big thing is the safety. The fact that there is no coolant to get rid of in order to have a meltdown or a problem. And of course, drainable, and I'll give you an example of that. If you have this very small reactor core and you leave a tube out there, and this is very hot liquid, as long as you keep that at room temperature by blowing some air across it, or in this case helium, forced helium tubes, that salt will freeze and it will make a plug. If you got a crack in this thing, actually it will leak out and probably seal itself, okay, depending on how the design of this is. But the point is if you lose power, if anything happens, somebody throw a grenade in this thing, or if this gets hot, too hot for any reason, that plug will always melt and drain into a passive pan, which can hold the heat and the radiation. If everything's okay, just heat it back up or even turn it right back on, and it's liquid state. It takes a little while for that heat to dissipate, and you can pump it back in and start up. So instead of being like really cautious about shutting down your reactor because you'll black out half the neighborhood or whatever and take days or months, if not years, to restart, you can go ahead and shut things down and go, oh, it was just a mistake, and immediately go back online. So actually there's an inherent safety in there because you can use your safety system all the time. Actually, I need to go back. All right. We'll pick thorium. Thorium advantages here, that it was abundant. I mentioned that. The fact that it's not fissile, okay, it means it's not weapons usefulness, in which case the less terrorist interest, again, goes to cost and safety, security, can't explode. Look at the uranium cycle compared to the thorium cycle. You start out with a whole lot more mining with the uranium cycle. You have a whole lot of yellow cake that you make. Everybody recognize that. But then you got to enrich that and then make these pellets. It's a very expensive process. The security to do this process is very expensive, much less the actual process. You end up with a whole bunch of depleted uranium. It's still useful in some ways and not useful in others, so I don't know what people are doing with that other than letting it sit on the ground. It doesn't go to Yucca Mountain. You need a very big plant. As I saw before, a very large reactor with a vessel that can hold up all the steam or any explosion that can happen here because it's very high pressure. Big turbine plant next to it, and you produce a whole lot of spent fuel, and you need Yucca Mountain for 10,000 years. The thorium cycle, you need 1 ton. This is for the same amount of energy, 1 gigawatt for 1 year. Much smaller plant, low pressure. The Braytons are much smaller, much more efficient, as much as 50% efficient or better, compared to about 35% best you can do for steam. 1 ton of fission products, but the big deal here is that within 10 years, most of that, 83%, is going to be back down to safe background levels, which means you can take those products, which actually were produced in the reactor. There's some very interesting things you can get out of that, and you can sell some high-quality materials. And the remainder only needs 300 years approximately for storage, which you can imagine that finding in many places around the world that can handle that, and you can imagine making storage vessels that are, caskets that can last 300 years. Well, proliferation risk, one of the things that happen with this particular process, with the litho process as we see it, there's going to be a little contamination of uranium-232. You just can't help it. I'll show you that in a minute. And it has a decay chain that gets you down to thallium-208, which has a hard gamma emitter, which makes it very nasty stuff to deal with. This is where the uranium gets in. The 232 becomes, there are certain reactions that can happen. I don't have time to go through the details. If you have 1% of uranium-232 in the material and you're holding it, you have about 3 minutes, I believe, a little less than 3 minutes before you get your full 5 rem dose, which is considered, your top level. I think it's within half an hour you're feeling the effects of radiation poisoning, and within 2 hours you're probably likely to die. So it's very hard to handle. It also means separation. If a nation wanted to use this as material for weapons, it would be a hot enrichment environment to deal with. The radiation hurts the electronics as well as the explosive material within the weapon, so they don't they're long, not very long half-life as far as the shelf life of the bombs. So. Okay. On the fluoride salt itself, ionic chemical stability is very important, and I'll show that in a minute. The fact that it's very high temperature and low vapor pressure means you run very high temperatures. And again, each one of these things, room temperature solid, like I explained before, leak resistance, etc. So look at the radiation damage in a conventional nuclear nuclear reactor. It's going to have cladding. All the temperature and heat is built up within that cladding, and that cladding can't break. So, or you lose the noble gases, the krypton and other things which are radioactive. And so you end up having to pull out this core all the time and not burn up all the fuel, because there's physical damage being done to the solid. Whereas if it's ionically bonded in a liquid, the ionic bonds don't care. They're going to move around as they need to and reassemble, and you always have that ability to withstand a lot of punishment in the reactor. Another point of this is that the salts are actually very low corrosion, and the way to briefly demonstrate that, here's a typical salt in the reactor. And the larger the number, the better, minus 104. And this is the free energy, Gibbs free energy here. Chemists will say you need a difference of 20 between it and, let's say, a wall material or a vessel material, such as here's iron. And you can see that's about double the difference between those two. So it's pretty chemically stable, considered almost a noble chemical reaction in the reactor. Okay. Internal processing, we have minimal physical inventory, so the reactor's small. There's no fuel fabrication. Obviously, that drives a lot of your cost. And a big thing is you can extract both poisons and valuable materials out of the reactor. This is a little more detailed than the one I had before. What you're doing is you're pumping out of the core and you fluoride, just fluoride gas, through this salt. And all the uranium products are going to come out as uranium hexafluoride, which means it's a gas. And you pull it out and reintroduce any of the uranium that's not burned into the reactor. The rest of the salt goes through. You can vacuum distillation, get out the fission products. And what's left here is you can separate this. And this would probably take an economic analysis of how much time and effort would you do to separate these things. Do you do them at a central location plant where you take little bottles every once in a while out and centrally process? Or do you incorporate it like you do the actual breeding process within the reactor itself? This would all be self-contained in a reactor vessel. The blanket, on the other hand, comes out, and I like to think that is it's a reactive extraction column. If a chemist, it's like a catalyst, but they say that's a bad word, so don't use it. Well, to me, it's a catalyst in nature. The fact that you put in the thorium up here, and the thorium will go back into the blanket salt and replace the protactinium, which can be extracted out and put in a decay tank. Same thing here. You just flow gas through that, fluorine gas. All the uranium that's produced, whenever it's produced, is able to be put in back into the salt and back into the core. And very quickly on the closed cycle Brayton, just to say that it could be air-cooled heat rejection, as well as variable input pressure allows you to play with the size and the efficiency of the system. And this just shows, this is the advanced boiling water reactor typically looked at. And again, a very large building, no matter how you do these things. The lifter concept would be very much smaller. The whole reactor core would be something that size, with the entire Brayton system not much bigger. And then just shows, again, the difference in size of a comparison of a Brayton system versus steam plant, and some of the listing of reasons why you would think that the cost of this whole system would be significantly less than existing nuclear power plants. Okay. Well, the disadvantages, I think I explained some of these. It's unknown. It's going to be different from what the existing infrastructure is going to support. It does need a charge of uranium-233 or some other fissile material, but we suggest doing that because it keeps the whole reactor clean. And here's a comparison. Basically, I've covered most of these, everything from the waste, relative waste, 1/30th, 10,000 years versus 300 years. The fact that you can burn almost 100% versus 1%. The best reactors are planning a couple of percent, maybe 2-3, of the total fuel usage, as well as being higher efficiency, lower pressure, air or water cooled. And the unique applications, this should scale down as well as scale up if you want to make large plants, but it also could scale onto the back of a semi-trailer, that size, typical. It would obviously be very advantageous to the Navy, because even in their smaller vessels, they can't build their existing reactors to fit into the littoral ships that they have. We like to talk about submerged units because they're really not seen. You can put them in rivers, and they're very small, very invulnerable to attack or other things. And then if you really want to use other processes, high temperature directly from the reactor is very useful for, one is mobile. It can go to a site for shale oil extraction. It couples very well with desalination for water processes, hydrogen production as well, because of the high temperature nature of the reactor core. So hopefully I've covered the brief background. These are the main things that we try to achieve with the technology. Those are the driving goals, and then how you actually put the reactor together, so the specific details are driven by what you're trying to get out of it. And the primary reason why most people look at thorium is because of the unique nature of being able to produce a huge amount of energy for a very small amount of resources per megawatt being produced, and can readily be put together fairly quickly. So at this time, I'll take questions. Yeah.
The U-233 that's re-injected in the core, how do you keep the 232 out of it? I mean, it seems that you introduce 232 and it's something you don't want to go anywhere near.
What happens to the core when you introduce the 233 and the 232 in the reactor core? Well, first of all, a reactor, any reactor, is very, very hot. You can't go near it. It's going to have a lot of radiation going on. So adding the 232 in there is not making any significant difference in the overall radioactivity in the core itself. Technically, it is a small poison. It sits in there, but it's a very small trace amount. It's when you take it out that, unless you separate it out, you always have a hot uranium. And the difference is the separation is chemical separation versus the uranium-233, which is what you want for the weapon, and uranium-232, which produces this gamma all the time in its decay chain, has to be done with separation techniques that are more common to weapon development. Did I get the question right and answer?
I was just wondering if it makes the design of the reactor more difficult, because the 233 is actually part of the process. So, you know, the materials you would use, for example, as part of the plumbing, would you run into problems if your plant becomes contaminated with some 232?
No, because there's, again, the question was, is there an issue with the 233, 232 in the reactor core, or as it comes out through the piping because of this radioactivity? The decay products in the reactor overwhelm that. That's just one small source. The reason why it's significant for proliferation issues is the fact that it's hard to separate because it's from the stuff you want, because it's still uranium chemically. As far as the reactor itself, any of the pumping, the pipes, and everything else is going to see some level of radioactivity just because of the decay products. Those decay products, what's nice about this reactor, are always kept at a minimum because you can take them out. The gases, anything like krypton or whatever, comes out in the pumping process. So it's actually a cleaner reactor, if you want, inside the reactor, and wears and tear radioactivity-wise less. Yes?
What's your estimated cost for the consumer, say, I don't know, wholesale price or retail price at the meter, and then what are the barriers to pursuing this?
What is the price at the meter at the end of all this? We haven't gotten that far in economic development of what that would be. The argument here is that the technology and the research has been done, and there is a systems engineering point of view that you will say it will be less expensive. Exactly, we're estimating 20 to, I think I said 30 to 50% less, a more specific design. Remember, everything's being done on everybody's own time. This is a grassroots effort that, you know, we hope that somebody, whether the government or somebody else, wants to pick this up. It's all free knowledge. But it's a great question. Did I answer the other part of the question? Was cost of electricity, and then?
What are your barriers? So basically, resources, funding, what?
Oh, what are the barriers to put this together? A couple of them. One of them would be that, you know, the nuclear industry is run by the government. You're going to have to get government blessing on something, unless you leave the United States or whatever. There are other countries that are looking into thorium, but again, not significantly. And so I think the barrier is you know, those type of things. It is a nuclear process, and you're going to have to deal with the proper regulations to meet that. You know,
I thought I saw one of your slides that had a
Negative, yeah, let me go back to the slide. Basically, it's the ability of the reactor to respond in producing less power as the temperature goes up. So as the reactor core, a normal reactor, when the temperature goes up, okay, there's usually the core temperature, what do you call it, is moderated with the water, and you get less power being produced, okay? Maybe you flow more water through the reactor, for example. This expands itself. The core being liquid squeezes out. The less density you have, the less fuel you have in the reactor, therefore the less energy you can produce. So it's based on thermal expansion and how much fuel you actually have in the reactor. The same token, if your generators are producing more electricity because there's a higher demand, it sends back that fluid colder, which is denser, and therefore it will have more energy. And it is a natural process within the reactor itself. That's a common nuclear, I guess, determination of how safe a reactor is how good that coefficient is. Yes.
What are the engineering challenges involved? Like, it strikes me that, pumping extremely hot in both senses of the word salt through pipes and pumps and such might be a really difficult thing to do. Could we build one of these very easily?
The engineering challenges, I guess, is a question. Pumping hot salts through pipes and those kinds of things. We do that on a regular basis in industry. A lot of processes, a lot of industrial processes use the same kind of hot salt chemical industry uses. So there's precedents. There's pump manufacturers that do that kind of thing. The temperatures are hot, but not something that's not done every day in commercial industries. Obviously, the safety requirements for everything, you are talking about a nuclear reactor. It's going to have to be really good pumps, and the paperwork is a mile high to make sure those pumps are adequate. But again, even if the pump failed, it doesn't. You can drain the tank, and it will naturally get hot if the pump stops pumping. The core will get hot, overheat, pour out into your tray, and stop it for you. So there's nothing inherently that industry can't do. It is a big systems engineering problem to make one that's cost effective, that's safe and meets all requirements, and that all the little details were taken care of, but nothing that we've seen. Yes?
Yeah, so I've read that there's some kind of Gen 4 reactor development thing happening, I don't know, worldwide or something like this. There's like 6 different designs that they're pursuing, and this is one of them. But can you tell us a little bit about what that is? Like, to what extent does this get funded? Are the designs all being pursued with the same vigor? What's going on?
The question being, what is a Gen 4, or how does that play in with this? Gen 4 is a Department of Energy initiative. It's probably a good one in some ways. They're looking for what's the next generation reactor. Technically, molten salt, not lifter, which is slightly different, is under their category of Gen 4. My personal take on it, when I look at the amount of money they're putting in, I'm not sure they're very serious. I think it's in the realm of, and don't quote me, but $40,000, which is enough for one person to go out and write a paper and go to a conference. Whereas the other projects are getting much more serious money. I'll let other people decide what the track record of Department of Energy is and solving energy problems at this point.
So Kirk Sorensen's got his blog on the web, and I do that. So that's one sort of nexus of work on this kind of thing. I suppose you know him?
Yes. Kirk Sorensen and I are, this is our lifter is that, and that Thorium forum is probably the key repository in which people all get together and work on.
France, and then there was Per Peterson up in Berkeley working on this stuff. And I'm wondering what
there are several people that you're asking who else is working Thorium.
Per still working on this stuff, or did he lose all his funding and go do something else?
I think he's kind of moved on to other things. He was Department of the Energy, I believe, so I don't really know total status. Everybody's got their little ideas of how you use thorium, and some of them or just add thorium to a reactor, the existing reactor, and qualify that fuel. Now, qualification of a fuel for any reactor is a long, expensive process. And the question is if you're going to spend all that time and money and put it into the commercial reactors that are running fine and are safe, I would say maybe that's a little too much money, a little risk you're doing, trying to add it. But that is a solution for thorium. Thorium in a pebble bed is another one that people have talked about. It's a little bit better than maybe the conventional reactor. It's looking more and more like a liquid system. My point is I think you should go to liquid system and burn all the fuel because in a pebble bed or these other concepts, you don't burn all the thorium and you still have a lot of waste that you have to get rid of. So, yes?
Conceivably designed, built through private funds, or is it something that you have to have government funding and involvement for?
Private or government funding? Well, that's up to individuals. Again, the organization, loose organization that I'm really representing or working with, doesn't have an answer to that. It would be daunting for private funding. It could be done private funding. Certainly, the Navy would be a prime example of wanting something like this, yet the Navy has the same problem that Department of Energy does. They're kind of fixed in a certain pattern. It's very hard to break that. So if somebody wants to take it to the next step, which is maybe demonstrating the chemistry without the nuclear material, a private company would have to have some backing from the government to say, yes, you can use uranium-233, which there's actually a lot of stored, and they want to blend it down and throw it away. That's a sad way the government is looking at this. They haven't done it yet, but there are plans for it. So if I was a private company or a private funds, the first thing I'd make sure is I had somebody in the government side saying, yes, we will hold that fuel, and yes, we will let you utilize that. Because you need some kind of seed fission material in order to start the process. Okay. Any other questions? All right. Oh, one more.
So you're not currently pursuing any kind of path to make it? I mean, you're obviously making it visible, but is there a concrete path of, getting the government to go in on this, get research?
There are efforts. I guess your question is, what are the paths that we're pursuing or paths that could be pursued to get this going other than the education process that they were attempting to do right now? Yes, there is. There's attempts to talk to people both in the government. When I was in the Naval Postgraduate School, the students did a design project and found that it was very interesting what it could do for the Navy as far as capability in ships. We need to do some more studies like that. I suspect that is going to come out. I think in the next 6 months, because of all the energy research that's going to be done or analysis that's going to be done to find out which way we want to go, that thorium will be, and Lifter specifically, will be thrown in that mix. What comes out or who stands up and says, yes, let's do this, or provides funds to do this, that remains to be seen. And I talked to other people, privately about, what specific paths we've done, and share that information. Okay. No one, last minute question? One more. All right.
It seems like if the problem is kind of a bureaucratic mindset roadblock, going to the top, and Obama has said that he's not anti-nuclear. Go to the administration and say, look, we need to consider this and we actually take it seriously.
Yeah, going to the top. Again, not really a question, but a statement of going to the top all the way. The new administration and getting them to look at this and point the agencies or money in that direction. Certainly would help. I mean, that's the easy path if we can do that. People are working on those kinds of things. Like I said, I think it's a credible story, enough to keep it in the mix, enough to look at it seriously, and enough to seriously look at why has it not been promulgated to this point. What are those roadblocks, and is it just the bureaucracy that we have? That's a good question. Okay. Thank you very much.
welcome. Thank you.
Thank you. That was a great introduction. It's a blessing to be here. I have a lot of material to go over, so I'm going to dispense with some of my normal comments and jokes and go right to it. I plan to be talking about this in context of fusion, but I'm going to hold back some comments for there to get through the material and get to questions. One note in the beginning, I'm come here as an individual. I don't represent any agency or organization. There's a loose-fitting group of people around the country, mainly specialists, technologists that are interested in this field, both in energy and in particular thorium, and that we all have day jobs, fortunately good-paying day jobs for the most part, and so we come to give this information out freely and examine this idea and the use of thorium as an energy source. Outline, just going to mention that I talk about systems engineering because I've taught that in States and break it up into 100. You get 100%. So you can see oil is around 40%, and that line is the thickness equivalent to that. So you can see that most people would say we want to increase these desirables, okay? And notice the desirables are pretty thin, and it's kind of hard to increase them. These are the ones we probably want to phase out more, as well as less oil. We have huge energy losses in electricity production, about 25% efficient overall. Conservation is great. Do it at home. Most engineers, if they don't have to create any increased entropy in the universe, they would like to minimize that. But at the same token, you can see that we've paid the price up here, and that conservation, as much as we want to, there's not a whole lot of gains there in these two areas. The other thing is, if you notice right here, you can't make that line go to zero. Thermodynamics says you always have to have a cold
Welcome, everybody. I'm going to try to be short because we're running a little bit late, and then there is a talk after us. So today we're going to have a talk about, alternative energy. I think it's important. I think if we really want to make a dent in CO2, we need to be looking at some serious stuff as well. And for this purpose, we have today Dr. Joe Borrometti, and he is a NASA chair professorship. He held a NASA chair professorship position at the Naval Postgraduate School. He worked at NASA for 10 years as a
as well as my thermodynamics and nuclear background. You'll see a little bit of that. Some assumptions. I'm assuming that most people understand the energy crisis. It's global in nature. It's nobody's got a quick fix, at least nobody who agrees what the quick fix is. Thorium is not going to be commonly known, especially as an energy source. Increased electrical capacity is very important to the overall energy consumption. And the last thing is energy equates to the state or the standard of living. And one of the last green energy forums I was at listening to, they equated to 58 slaves, if you will, working full-time at hard labor, 365 days a year, for each person in the United States. And you can see that that level of energy is what gives us a standard of living. This slide comes from Lawrence Livermore Laboratories. It's one that I would spend a long time on. I think it has a lot of great points to be made. I would just say that if you don't know what a quad is, 10 to the 9th BTUs, it's a lot of energy. And if you just take all the energy we have in the United States.
Technology manager, lead systems engineer, nuclear specialist, and propulsion researcher. He's basically a rocket sciences guy. He there managed the emerging propulsion technology area for in-space systems, the Marshall Air Launch Team, as well as a variety of other power and propulsion assignments. After earning a doctorate degree in mechanical engineering from University of Alabama in Huntsville, he spent several years as a research scientist and senior research engineer at the UAH Propulsion Research Center, where he served as a principal investigator and manager for the Solar Thermal Laboratory. He has worked as a senior mechanical designer at Pratt & Whitney, supporting aircraft engine manufacturing, and at the Lawrence Livermore National Laboratory within the Laser Fusion Program. He's a graduate from the United States Military Academy. I think you'll find out that he knows what he's talking about, and I am eager to hear what he has to say. So please give him a warm welcome.